Welcome back. We've come a long way. We've crushed the gate, architected the liquid phases, and boosted the signal. Your sample is pure, and it's concentrated. But for those of you heading toward gas chromatography, or GC per megasiemens, we have one final, invisible wall to climb. Some molecules, no matter how hard you try, simply refuse to turn into a gas. They are too polar, too heavy, or just too stubborn. Today, we are going to perform chemical surgery to give these molecules wings. Welcome to the world of derivatization. This is the grand finale of our sample preparation journey, where we bridge the gap between biological messy reality and high vacuum detection truth. Imagine you have a high-performance jet. That's your GC instrument. But your molecules? They are like penguins. They have the right spirit, they are full of information, but they simply cannot fly. They are sticky. They have hydroxyl groups, amines, and carboxylic acids that create intense hydrogen bonds with each other and the column walls. They'd rather burn and char in your inlet than turn into a gas. In mass spec, this is a crisis of volatility. Derivatization is the chemical makeover that turns your molecular penguins into high-flying eagles. We are going to chemically modify those polar groups so the molecules become greasy, light, and ready for the vacuum. To master this makeover, we categorize our chemical surgeries into three primary tactics. First, the silicon shield, silylation, which is your universal toolkit for metabolomics. Second, the fluorinated spear, acylation, designed when sensitivity is the priority. Third, closing the acidic gap, esterification, for lipids and organic acids. Finally, we will confront the specialist's nemesis, moisture. We move from the macro view of flight to the micro level of functional group modification. A specialist chooses the surgery based on the patient's or molecule's specific polar needs. Let's start with the most common tool in our arsenal. If you work in a metabolomics or drug testing lab, you will likely reach for silylation first. Why? Because it's the universal suit. We take active hydrogens, those pesky ones on OH or NH groups, and replace them with silyl groups, most commonly TMS. Look at the animation logic here. By placing that bulky silicon shield over the polar oxygen or nitrogen, we effectively kill the molecule's ability to form hydrogen bonds. We reduce the dipole-dipole interactions. Suddenly, the molecule doesn't want to stick to its neighbors or the glass walls of the column anymore. It becomes greasy and volatile. It's like putting a wax coat on a penguin so it can slide through the water, or in our case, the carrier gas, at high speed. A common mistake is thinking you need to bake these reactions for hours. A specialist knows that BSTFA and MSTFA are fast. Usually, heating to 60 degrees C for just 15 minutes is the sweet spot. If you go over this, you risk breaking down the very derivatives you just built. The beauty of reagents like BSTFA is the clean exit. The byproduct, trifluoroacetamide, is highly volatile and won't interfere with your early eluting peaks. You aren't just adding a tag, you are architecting a cleaner journey for the molecule to reach the detector in one piece. Have you ever seen a peak that looks like a shark fin? A massive tailing mess that won't resolve? That's not the machine's fault. That's a polar molecule begging for a makeover. This tailing happens because a portion of your molecules are sticking to the active sites on the column, or the glass liner. A technician just adds more reagent and prays. A specialist knows that tailing peaks mean your derivatization wasn't complete, or the molecule is too polar for the current column phase. It is a visual diagnostic tool. When you see a shark fin, you know your silicon shield is either missing or cracked. Sometimes, volatility isn't enough. You need sensitivity. This is where we use acylation. Instead of silicon, we add an acyl group, specifically one loaded with fluorine atoms, like PFPA. Here is the strategic advantage. It's not just about flight, it's about visibility. Fluorine atoms are massive electron magnets due to their high electronegativity. By adding a fluorinated spear to your molecule, you make it incredibly visible to an electron capture detector, ECD, or negative chemical ionization, NCI. Actually, this is how we detect trace levels of steroids or environmental toxins that are otherwise invisible to standard detectors. A specialist chooses acylation when they need to find a needle that is not only hidden but also very, very small. The increase in sensitivity isn't just incremental. With the right detector, it can be 100 times stronger than an underivatized sample. By adding that fluorinated spear, you are essentially giving the molecule a high visibility jacket. It makes the signal pop out of the baseline noise. Furthermore, in MS, these derivatives direct the fragmentation pattern, giving you a clear structural fingerprint. You are no longer just guessing at a mass, you are seeing a predictable story told by the fragments. A pro chooses this when they need audit-proof data at part per billion levels. If you are analyzing fatty acids, you are facing a GC column's worst nightmare. A naked fatty acid has a carboxylic acid group that is so polar, it will practically weld itself to the column's stationary phase. To fix this, we use esterification. We perform a rapid surgery, often using BF3-methanol, to turn those acids into FAMEs, fatty acid methyl esters. A technician follows the recipe. A specialist understands that without this surgery, your fatty acid profile would be nothing but a flat line and a ruined column. We are closing the polar door so the molecule can run the race without getting stuck to the starting blocks. This surgery is lightning fast. In just 2 minutes in a water bath, you've neutralized the acidity and lowered the boiling point of the entire sample batch. It is the gold standard for nutritional and lipidomics research. But remember the specialist's rule. The efficiency of this reaction depends on the methanol purity. If your methanol is wet, the equilibrium will shift back toward the acid, and your makeover will fail. Speed is useful, but precision is what ensures the molecules actually reach the column. Now we must talk about the hidden red flag. You can have the most expensive reagents and the purest sample, but if you have moisture, you have failure. Reagents like BSTFA are chemically designed to react with active hydrogens. Guess what has 2 very active hydrogens? Water, H2O. If one single drop of water gets into your vial, it will consume your reagent instantly, producing white clouds of silica or acid fumes. Actually, the difference between a pro and an amateur is how obsessed they are with anhydrous conditions. A pro uses sodium sulfate to dry the solvent and blows down with ultra-pure nitrogen. 1 drop of sweat or a humid day can ruin a $500 bottle of reagent and an entire week of work. Respect the dry, or the reaction will die. Use this matrix as your surgical prep guide. If you have an unknown alcohol in a metabolomics run, reach for your silicon shield, silylation. If you are looking for trace environmental toxins and your signal is weak, sharpen your fluorinated spear, acylation. If you're analyzing butter or oils, close that acidic gap with esterification. This isn't just about a reaction. It's about a laboratory decision that protects your instrument and guarantees your results. Don't force the instrument to adapt to the molecule. Force the molecule to adapt to the vacuum. By mastering these 3 surgeries, you ensure that any molecule, no matter how stubborn, can fly. We have performed the surgeries. We've used the silicon shield for volatility, the fluorinated spear for sensitivity, and esterification for acidity. You are now a master of molecular flight. Remember, a specialist doesn't just add a chemical, they engineer a signal. You have built the foundation of truth by ensuring your sample is ready for the instrument. You have completed the sample preparation phase of this course. You've cleared the noise, boosted the signal, and now you've made the molecules fly. You are ready for the race. You've mastered the art of preparation. Your sample is pure, concentrated, and now it can fly. You have built the foundation of truth. But having a fast car doesn't matter if you can't drive it through the traffic. It's time to let the race begin. Join me in our next module, Module 3-1, the molecular race, where we move from prep into separation. We are going to learn how to control how chemicals behave under pressure in the chromatographic column. I'll see you at the starting line. Any final questions on making your molecules fly?